Hello and welcome to the season 2 of RATA Skillathon. RATA Skillathon was a project which was started last year, and it happens in the month of July, which we consider as the least pressure months, or in terms of the weather, it is probably with a lot of monsoons around. So we said, why don't we spend this month about training ourselves and skilling our people? So when it came to that, we decided that we should get the best trainers in town to do a session online. And this is available on YouTube. It's always available to you. But if you're a RATA member, even after the live session, you can see it through your members login and use it multiple times for training and learning. So the idea is, how do you actually gain skills at literally no cost from the best people in our industry? So today we have a very interesting session, which is CO2 as a refrigerant. And we're very fortunate that we have Mr. Gangadhar from Danfoss, who's taken time out to actually share his knowledge and explain to us that how CO2 is evolving as a refrigerant. So Mr. Gangadhar, thank you so much for taking time out and being with us today. And we're really looking forward to this session. In fact, I'm personally looking forward for this session because this is going to be a lot of knowledge sharing. So yes, thank you very much. And over to you, Gangadhar.
Thank you, sir. So, good evening. So one and all. So I am Gangadhar. So I've been working in Danfoss as a assistant manager for CO2 applications. So I've been associated with Danfoss from last 1 year. So I have been working in this refrigeration industry from the last 8.5 years, and especially in the design and development of refrigeration systems, both in HFC, ammonia, CO2, complete design and development of refrigeration systems. So in this session, we would like to learn about more on CO2 as a refrigerant. So what is CO2 and what is CO2 refrigeration, and how CO2 refrigeration is differ and differentiated from all other refrigeration systems in the industry. So we can be able to go through the complete CO2 applications where we can be able to effectively utilize CO2 refrigeration systems in current Indian market and based upon the Indian applications. To start with, so CO2. First, we will understand the CO2 thermophysical properties and what is the global warming potential number for it. And apart from that, like, we can be able to understand the pressure enthalpy chart where the CO2 can be able to the limitations of it. If you can see CO2, first of all, it is a natural refrigerant. So be like ammonia, so it is also widely available in the nature. So this is having the ozone depletion potential is 0 and global warming potential is 1. It is a completely non-flammable and non-corrosive refrigerant and easily available everywhere, and it is having the high heat of compression and low cost, and it is cheaper than other conventional HFC refrigerants. So to understand what is the global warming potential with comparison of other refrigerants, for an example, we have a reference of HFC refrigerants such as R134A and R404A, and we have ammonia also. To compare the CO2 with other refrigerants, where we have global warming potential of R134A and R404A is 1300 and 3260 respectively. And the CO2 where you are taking as a reference to calculate the global warming potential, and CO2 having the global warming potential of 1. If you are comparing the critical point and triple point, if you are understanding what is the critical point and a triple point, first we'll understand what is critical point. If you're seeing in the left bottom, there is a pressure enthalpy chart. So in this pressure enthalpy chart, uh, there is a liquid and there is a vapor line. You can see here the leftmost part is liquid, the yellow color one is liquid, and the rightmost part is vapor. So the critical point where there is no clear distinction of the liquid directly convert to a vapor and there is no phase change, where this is happening, we call it as a critical point. Generally, all conventional refrigerants having the critical point higher than their condensing temperature. For an example, if you take R404A refrigerant, the maximum condensing temperature we are going up to 55 degrees centigrade. So it is having, when it is entering into the condenser, it will desuperheat. After that, there is a phase change, and after that, it is subcool. So there is a definite amount of phase change will be happening in the condenser, because all the HFC refrigerants what we are dealing, or even ammonia refrigerant also, the critical point is always higher than the condensing temperatures. But if you can see CO2, the critical point is itself is 31 degrees centigrade. If you, for an example, if you take India like atmospheres, tropical conditions, the ambient temperature itself and on average of 30 to 35 degrees centigrade. Okay, so if you are taking the 31 degrees centigrade as a critical point, we cannot able to operate the CO2 system as a single refrigerant in subcritical, as a subcritical system where you have a clear desuperheating, phase change, and subcooling. And if you are seeing, that's why all our CO2 systems will be operate in supercritical region, where you you could not able to have clear distinction of liquid and vapor. So if the system is operating above the critical point, we call it as a supercritical region, or it is a transcritical region. And one more point we need to understand is the triple point. So what is triple point? Triple point is a state of a CO2 where it all the three phases such as solid, uh, vapor, and liquid will be established in one equilibrium that we call it as a triple point. The triple point of CO2 is in general is minus 56.6 degrees Celsius at 5.2 bar. So below the triple point, there is no liquid, only solid and vapor phases will be exist. Okay, above the critical point, there is no clear distinction of liquid plus vapor phase change. Liquid is directly converted to a vapor. So these are the definitions of critical point and triple point of CO2. So CO2 is first of all non-flammable and non-explosive refrigerant, and it is a non-toxic refrigerant. If you are seeing the ASHRAE 34 toxicity and flammability chart, the R744 or CO2 is an A1 refrigerant, and it is nearly having the approximate 0.04% volume in the atmospheric air. So first we will understand what is the kind of systems we can do with CO2. So in CO2 in general, we can use as a two different kind of systems. One system is subcritical CO2. So another system is transcritical CO2. For an example, let's understand the subcritical CO2 system. Subcritical CO2, when a CO2, if you want to operate in a subcritical range, then obviously we need to operate the condensing pressures below 31 degrees centigrade. So for that reason, we need to take another refrigerant as a help to behave the CO2 in a subcritical region. For an example, I want to operate my CO2 evaporator at minus 40 degrees centigrade. Then I need to design a system where there is a cascade heat exchanger. In this cascade heat exchanger, the condenser of the CO2, the all the heat that is rejected to my one more refrigerant on the higher side, that may be a freon refrigerant or that may be an ammonia refrigerant. So if you are observing this cascade condenser, I want to operate my CO2 at below subcritical region or below the critical point, then I need to condense at below 31 degrees centigrade. So in general in industry, whenever I want to maintain my CO2 evaporator minus 40 degrees centigrade, then CO2 condensing temperature in general will be at minus 10 degrees centigrade. So at minus 10 degrees centigrade, CO2 will condense, and other side, if I take high side as an ammonia, okay, the ammonia will be operating at minus 15 degrees centigrade. So minus 15 degrees centigrade, ammonia will take all the load from CO2, and it will ammonia refrigerant will evaporate, and it is going to the ammonia compressor. That ammonia compressor will reject the heat to the my air cooled condenser or water cooled evaporative condensers. So this is a cycle where I can be able to use CO2 as a subcritical system. If you can see it in the below pressure enthalpy chart, in this one, minus 40 is my CO2 evaporation temperatures, and minus 10 is my CO2 condensing temperatures. Other side, ammonia will be operating at minus 15 as an evaporation temperature and plus 40 as my condensing temperature. So such a way that I can run CO2 as in a subcritical state. If I want to run CO2 as a single refrigerant, then I cannot able to operate in a subcritical mode. Obviously, I need to go as a transcritical CO2. So in this transcritical CO2, the conventional refrigeration system we cannot able to maintain, because in the conventional refrigeration system we have one compressor, condenser, and expansion valve and evaporator. So in the transcritical system, generally we have two more additional components. Those we call it as high pressure expansion valve and flash gas bypass valve. So with the help of these two components, we are trying to establish a transcritical CO2 system that can be able to deliver combined heating and cooling. So evaporation side, you can be able to get the cooling, and simultaneously condenser side or gas cooler side, you can be able to get the heating. For an example, how this system is can be controlled in a transcritical CO2, we will understand. So first of all, if you can see, this is the compressor. This we call it as a gas cooler. Why? Because if you see it in the right hand side, there is a pressure enthalpy chart. In this pressure enthalpy chart, the compressor suction will be operating at 28 bar, and the compressor discharge is operating at 90 bar. Okay. The critical point of CO2 is 31 degrees centigrade, and the corresponding pressure is 73.8 bar. So if I want to operate my system at transcritical, then I need to go more than my critical point. So 90 bar is my a compressor discharge pressure. At this compressor discharge pressure, there is no phase change because I am going above the critical point. At this point, I am only cooling the gas where it is in a supercritical region. So that's why instead of condenser in CO2, we are calling it as a gas cooler. Okay. So the gas is cooled from high pressure, high temperature to high pressure, low temperature. If you can see it in the right side, the pressure we are maintaining is same, but we are decreasing the temperature from something like 100 or 120 degrees centigrade to 30-35 degrees centigrade. So the third point where you can see is this is the point. From there, since it is having the very high pressure, 90 bar pressure, from the 90 bar pressure, from this point, if I directly use one expansion valve and directly dropping to my evaporator pressure, so the line will be straight line to here. So by doing like that, I will lose so much of energy. That is the first thing, and I will the evaporator outlet or expansion valve outlet, there is so much of flash gas formation. That flash gas formation will be very inefficient system design. That is the reason what we need to do is that from the high pressure, we need to drop by using the high pressure expansion valve to some intermediate receiver pressure. If you observe this high pressure expansion valve from the point 3 to point 4, we are dropping the pressure from 90 bar to some intermediate pressure, that is 34 bar in this example. From 34 bar in the receiver, there is a liquid and there is some vapor, because the fourth point which is operating at liquid plus vapor zone. So the liquid that is forming in the receiver, we are sending to the expansion valve, that is electronic expansion valve, and whatever the vapor that is forming in the receiver, that we are sending to the compressor. If you are observing the point where we are dropping the pressure from 6 to 7 through the expansion valve, you can see it here in the right hand side, and the pressure that we are dropping from 5 to 9, you can see it here in the right hand side. So the gas that is coming out of your flash gas bypass valve and the gas that is coming from your evaporator outlet, these two will mix up, will coming to as your compressor suction. So that is the point 1 in the pressure enthalpy chart. So this is a basic cycle. This is we call it as a gas bypass cycle. In this gas bypass cycle, we were dropping the pressure from high pressure to one intermediate pressure through our high pressure expansion valve, and whatever the gas that is forming in the receiver, we are bypassing through one gas bypass valve to the compressor. So this is a simple standard cycle for CO2 application. So here compressor, gas cooler, high pressure expansion valve, flash gas bypass valve, receiver, electronic expansion valve, evaporator. So all this one we need to be controlled through one controller that we can call it as an high pressure or AKPC controller, adapt cool pack controller. This pack controller will keep on measuring all the points, whatever the set points we are giving to the system, such as the pressure at the discharge, the pressure to the receiver, the pressure to the evaporator. So all this one, it can be able to maintain and control. So similarly, there are multiple different systems are there for CO2. For an example, booster system, it is called it as, there are two different compressors we are using here. One is for the booster compressor, another one is the empty compressor. For suppose I have an application where I need one evaporator at -5 or -10 degrees centigrade, one evaporator at -45 degrees centigrade. If that is the application, then I can use a booster system where -45 evaporators will be operated on booster compressors. The booster compressor discharge is going to my high stage compressor suction. So my high stage compressor empty evaporators, we in general we call it as, this is empty temperature or medium temperature evaporators. This we call it as LT or low temperature evaporators. So my medium temperature evaporators are operating at -10 degrees centigrade, and my low temperature evaporators are operating at -40 or -45 degrees centigrade. So the -45 degrees centigrade gas is taken care by booster compressors. The booster compressor will discharge and it is going to my empty compressor, empty evaporator suction, evaporator outlet. These two will mix and it is going to my empty compressor suction. So empty compressor suction will discharge all this heat to the gas cooler, and the gas cooler outlet, these two are same. This is the high pressure expansion valve and this is a flash gas bypass valve. So like this, I can be able to maintain, or I can be able to give the different evaporation temperatures according to the customer requirement. So this is a booster system. In similar, there is a parallel compression system, an HP ejector system, liquid ejector system, and LP ejector system. So there are multiple configuration of systems are possible with CO2, where all these systems are enhancing the COP of the system and efficiency of the system. So these are all our advances in the CO2 technology, where you can use the one parallel compressor, and where you can inbuild one ejector, or where you can inbuild 2 3 ejectors in the system by increasing the enhancing the efficiency of the CO2. In general, the main basic application of CO2 is in general in India like countries, uh, for refrigeration, only refrigeration. For suppose I need one -40 or -45 degrees cooling capacity at maybe 100 kilowatt uh, requirement. If there is only cooling requirement, then there are number of conventional refrigerants are there in industry. For residential applications or commercial applications, mostly we are using the HFC refrigerants such as R134A, 404A, 410A. So all these refrigerants we are using for mostly for the residential or commercial applications. For industrial applications, mainly for food processing, fisheries, cold storages, and these are industrial. We are using ammonia as a primary refrigerant for driving the -40 or -45 degrees evaporation temperatures with 100 kilowatt or more than 500 or 1000 kilowatt of loads. But the CO2, the advantage of CO2 is CO2 is can be able to deliver a combined heating and cooling, where you can get at a time cooling and heating. For an example, let's take an example of simple flash gas based bypass system. So this is a simple flash gas based bypass system that we are already discussed, where you have one compressor, one gas cooler, and one high pressure expansion valve, receiver, flash gas bypass valve, electronic expansion valve, and evaporator. In this one, uh, the advantage of CO2, I can get at a time hot water temperature of 90 degrees and 7 degrees chilled water temperature. It is possible with CO2. Let's understand how. So this is your system. In this system, my evaporator is operating at, let's say, I have 50 kilowatt evaporator. Okay, so this is a 50 kilowatt evaporator. This 50 kilowatt evaporator, uh, to deliver, to compress it from, let's say, 5 degree evaporation temperature, which is equal to nearly 40 bar. So compressor is compressing from 40 bar to 115 bar. Okay, so when I compress the CO2 from 40 bar to 115 bar, obviously 115 bar is above the critical point. So 115 bar, the discharge temperature is nearly, if you can see it in the right side, that is 120 degrees centigrade. So if I am compress the CO2 refrigerant from 40 bar to 115 bar, the discharge temperature I will get is nearly 120 degrees centigrade. Now there is a gas cooler load that is equal to 80.7 kilowatt, nearly approximately 81 kilowatt. Okay, so this 81 kilowatt load, instead of I rejecting to the atmosphere through any air cooled gas coolers or any water cooled gas coolers, I would like to recover all this heat to the water. For an example, in an industry, there is a boiler, and that boiler is used for generating the hot water of 90 degrees or 100 degrees centigrade. Similarly, in the same plant, customer having the requirement of chilled water also. Then instead of taking two separate system, one is for the heating boiler for the heating, or any freon chiller for the cooling, if we consider the CO2 heat pump, the single CO2 heat pump can generate 90 degrees hot water temperature and 70 degrees chilled water temperature at a time. If you can see here, the 120-degree temperature, we are cooling down the CO2 to up to nearly 35 degrees centigrade. Okay, so this is the condition where the inlet temperature is 120 degrees centigrade, the outlet temperature is 35 degrees centigrade in one side of heat exchanger. So other side of heat exchanger, I am using the water. That water is entering at 30 degrees centigrade. So similarly, the water, I can be able to get a 90 degrees hot water temperature in a single pass in a heat exchanger. That is way more possible with CO2. Why? Because if we are seeing in the pressure enthalpy or temperature enthalpy chart, in this temperature enthalpy chart, the red line, this is the isobaric line or pressure line, constant pressure line, where this is all the heat I am able to recover from the 120 degrees centigrade to 35 degrees centigrade. That is the CO2 temperatures inlet and outlet. The blue line where you are seeing is the 30 degrees centigrade water is all the way going up to 90 degrees centigrade water. So because of so like abundance heat that is available in the transcritical region, I am extracting all the heat by utilizing water and the other side. So in similar, high pressure expansion, this cycle is already constant. We have already discussed this cycle. So this is your electronic expansion valve. In that electronic expansion valve outlet, you will get the, and my compressor is maintaining at 40 bar suction pressure, saturation suction pressure, which is equal to 5 degree saturation temperature. So 5 degree saturation temperature, where we are having the empty evaporator and maintaining, so that if the customer is requesting air conditioning also, then I can get 7 degrees chilled water temperature from my heat exchanger. This 7 degrees chilled water temperature, I can utilize it to my air conditioning. So in a single CO2 system, I can get heating also. At the same time, I can get the cooling also. So this is the way we can be able to utilize the CO2 heat pump in an application where we have a combined heating and cooling requirement. This is CO2 heat pump, one more application. In this application, it is possible with the CO2 to get even 120 degrees centigrade high pressure and high temperature hot water. For an example, if you are maintaining the water side, first of all, this is the water side. In this water side, if you are giving the water to the PHE at 3 bar or 2.5 bar pressure at 30 degrees centigrade, then you can be able to deliver nearly 120 degrees outlet temperature with the CO2 heat pump. It is also possible with few considerations where there is a term called pinch point. We need to understand the pinch point. The pinch point is the point where the smallest difference, temperature difference between the primary fluid and the secondary fluid. Here, primary fluid is the water, and the secondary primary fluid is the CO2, and the secondary fluid is the water. So where it is having the smallest temperature difference, there we can be able to get, for suppose if you can see in the one line here from 30 to 60 degrees centigrade and 60 to 120 degrees centigrade. So we are utilizing two heat exchangers. One heat exchanger will deliver 30 degrees centigrade to 60 degrees centigrade, and other heat exchanger can be capable to deliver the remaining water from 60 degrees centigrade to 120 degrees centigrade. So such a way that we are distributing the heat condenser heat or gas cooler heat to one heat exchanger that is delivering nearly 30 degrees centigrade to 60 degrees centigrade with different flow rate. One heat exchanger will give you the different flow rate, other heat exchanger will give you the another different flow rate. So, where we are using this kind of application, for an example, in a customer kind of requirement where you have food processing units or fisheries units, so they can utilize the generally they have a requirement of 60 degrees or 55 to 60 degrees hot water for their floor cleaning or their mess cleaning or their different process requirements they having, and then require the 120 degrees hot water also for their IQF applications where they are using the cooking of processing of the shrimps or processing of the fish. All this requirement they have a requirement of 120 degrees hot water also. So at the same time, customer is also having the air conditioning where the processing areas they request the air cooling. So in this condition, they will get the three. They have a requirement of three utilities. One is 60 degrees hot water temperature utility, and 120 degrees hot water temperature utility, and another one is 7 degrees chilled water temperature utility. So all three we can be able to generate with the CO2 heat pump. Yeah. Just we will understand the working principle of the ejector. So how ejector is being can be able to integrate in our CO2 system, and how can this is uh, like um, deliver the better efficiencies. I just want to go back for one slide. Uh, if you can see this one in this slide, there is a flash gas. In this one, we can call it as a flash gas. This flash gas is generated. This flash gas is generated during the throttling process. This flash gas is no use in general because of the throttling only this flash gas is generated. We try to use the flash gas that is generated at the IP receiver in such a way that we can be able to reduce the power consumption of the compressor. For an example, if you see the working principle of ejector, whatever the gas that is leaving from the gas cooler, that gas is entering to the ejector, okay, from the nozzle here, and whatever the gas that is coming out of your empty evaporator outlet, this is the empty evaporator outlet, this gas will other side it will enter. When these two gases are entering into the uh, my ejector, the outlet of the ejector will be coming as one intermediate pressure. So in this case, what I will do, instead of sending all the gas from my empty evaporator outlet to the compressor suction, some of the gas I am bypassing to my ejector. So in that way, if I am bypassing some amount of gas from my empty evaporator outlet to the ejector, I can save some energy, power consumption on my compressor. So this is the working principle of ejector where gas cooler outlet pressure, that is with the flow rate, it is entering at one side. Another side, the empty evaporator outlet, some of the gas will entering at another side, the PL. When these two gases are mixing in the mixing unit, and where you can see here, there is a nozzle and there is a throat where you have a lesser diameter, it is causing the increase in the velocity and decrease in the pressure drop. When the pressure is dropped, then all the gas will mix up here and it will exit through diffuser. So in the diffuser cone, you can see the area is increased. So the velocity got reduced and the pressure got increased to some intermediate pressure. So that is actually the working principle of ejector. So let's understand the CO2 in general basic properties. CO2, it is having the high volumetric cooling capacity. Okay. So what is high volumetric cooling capacity means? Uh, the kilojoule per meter cube. Okay. The volume metric cooling capacity, we can call it as how much volume of bore of a cylinder of compressor it is required to generate 1 kilojoule. Okay. If more volumetric cooling capacity means I can end up with less uh, uh, bore of my cylinder. Okay. In CO2, in general, the volumetric cooling capacities are very high because the suction densities are very, very high for CO2 compared to all other refrigerants. And the specific volumes are way lower to the CO2. A small volume of refrigerant has a high capacity, and volumetric capacities are nearly 5 to 7 times greater than R22. This is because of this one, it is allows you very a smaller compressor, which is equal to 5 to 7 times lesser footprint compressor of CO2 compared to R22. Because of the suction densities are high and your mass flow rates are density into area into velocities, because of the higher density you will, by maintaining the same velocities according to the Ashley designs, you will end up with uh, a smaller pipe dimensions, smaller cross sectional areas of the suction pipes. Smaller compressor sizes are actually there. Why? Because you have a less footprint by maintaining the high volumetric cooling capacities of your compressor. We have an high pressure refrigerant that is a 30 degrees or 31.1 degrees centigrade, which is having the critical point, which is equal to 73.8 bar. So effect of pipe pressure drop is very low because in general for CO2 the uh, the pressure difference dp by dt, the pressure with respect to the temperature drop is like very high, like one nearly 1 bar pressure is equal to the 1 degree saturation temperature. For like unlike ammonia, it is like zero point 0.1 bar or 0.2 bar with 1 degree saturation temperature. So even if it is a small temperature or a small pressure drop in ammonia, it will give you the a large 1 degree or 1.5 degree saturation temperature drops. Because of this saturation temperature drops, especially more pressure drop means more saturation temperature drop, so it will give you a the your compressor will end up with operating at the low evaporation temperatures than required. Because of this one, your ammonia compressor's power consumption is got increased. But where in CO2, it is in contrast because the pressure losses are not much of an effect. Even you have a long pipes, it is having the maybe zero point 0.5 or zero point 0.6 or even 1 bar pressure drops also. It does not give you that much of an effect on the saturation temperatures. It is having the high density gas, as we are already discussed. Because of that high density gas, your heat exchangers are becomes very efficient. Because of this the rho value or density value, your overall heat transfer coefficient values of the CO2 is very very high. And apart from the high density, because of the effect of the high thermal conductivity, the low viscosity, all these are an added advantage, all these are an added thermodynamical superior properties of CO2, which makes your heat exchangers are very very efficient, and you can be able to achieve a low delta between water to CO2 or air to CO2. So that is the reason when you are operating at 5 degree evaporation temperatures of CO2, by maintaining even 2 degree delta between CO2 and water, you can get 7 degree chilled water outlet temperature. So 5 degrees is your CO2 evaporation temperatures and 7 degrees is your chilled water temperature. If you can see the advantages of the transcritical CO2 systems, for an example, the swept volumes, the whatever the CO2 compressor swept volume, the piston cylinder compresses, R134A compressor with respect to the CO2, you can observe here. And the CO2 compressor is nearly 6.7 times R, more than 6 times smaller compared to your R134A refrigerant. Because of the smaller pressure ratios also, because the 40 bar 115 bar, when you are dividing the suction to discharge, you are end up with the small compression ratios, which is also having the high compressor efficiency. And if you can see the gas cooler to condensing exit temperatures also in the right side, where your pressure ratios are lower for the CO2. This is the line. Because of the high suction densities, compact installations of CO2, and the high volumetric cooling capacities, your CO2 compressor, the piston size is way lesser than any other conventional refrigerant piston cylinders or pistons. If you can example, let's say I have a 20 kilowatt system with nominal operating conditions, with any saturation temperature of maybe plus 5 degrees or minus 10 or minus 20. A 20 kilowatt system with R744 piston, a Bock compressor. This is a CO2 compressor. SGX34 is the model. It is allows you to design at 20 mm stroke or 28 46 mm stroke with 4 cylinder, but the same way you can have 70 mm bore with 50 mm stroke. So it is nearly, you can see the bore to bore comparison. So CO2 where it is allows only 28 mm bore, but it is nearly 2 times of R134A piston, because the specific volumes of 134A or any other refrigerant is very higher in suction side, but when suction obviously densities are also lower for HFC refrigerants, but wherein CO2 the suction densities are way higher. That's why it is allows you to the volumetric cooling capacities are higher. So it is allows you to the a compact installations with reference to the CO2. Yeah. So you can see the advantages of transcritical CO2 systems, wherein it is also because of the higher suction densities, it is also allows you for the smaller vapor lines, okay, line sizes. Suction line, let's say for an example, 5-degree evaporation temperature with 5K superheat. CO2 vapor line, nearly you can see here, there is a 150 kilowatt system that is operating at 5 degrees saturation temperature, where CO2 is nearly way lesser than your R134A pipeline at the vapor sizes and vapor line sizes. See here in the 744, the nominal size for the 150 kilowatt is 1-inch line, but where in ammonia it is a 2-inch and it is a nearly 3-inch line, okay, in R134A. So like if you have a very long pipelines, and in that long pipelines you want to maintain nearly 200-meter or 250-meter long pipelines, there it's really CO2 pipelines are very smaller, so that the insulation is also very less, so that the losses to the ambient also very less, so that such a way that your CO2 system is works very efficiently when you are having the less vapor line sizes. As we discussed, the advantages of the transcritical CO2 system, the heat exchanger also, because of the overall U value, the overall heat transfer coefficient U value is way higher. It is nearly in thousands because of the high suction, high densities, and high thermal conductivity, low viscosity, and all these parameters are adding an advantage to be able to deliver high heat transfer coefficients for CO2, which allows you for the less delta between primary and secondary fluids, which can you can be able to achieve 1 degree or 2 degree pinch also, and the smaller heat exchange area For an example, the same example where 150 kilowatt and 5 degrees centigrade saturation temperatures, you have a 744 will end up with 15 meter square area, where other refrigerants can go up to 30 meter square and 50 meter square areas. So that is also one of the advantages for your CO2 heat exchangers, where you can be allowed a compact installations. So where we are actually seeing the application here, the application of CO2 as a refrigerant. So first of all, as we discussed, if there is a combined heating and cooling, for an example, if I need hot water at 90 degrees centigrade, at the same time, if I have a requirement of chilled water at 7 degrees centigrade also, then CO2 can be able to deliver uh, with these operating conditions. You can see, for an example, just like combined heating and cooling with air conditioning for residential and commercial buildings, where combined heating for shower applications or your residential applications. Food and beverage industries, mainly for the sterilization, we required hot water, and chilling of the beverages, mainly for the we require the chilled water. So pharmaceutical and process industry also, like you have a boiler. In that boiler is it is like maybe high temperature, high pressure boiler, like such as a 10 bar 185 degrees steam it is generating, but that steam has to be generated from 30 degrees centigrade water, correct? So instead of giving 30 degrees water to your boiler, you can give we can give 90 degrees or 100 degrees hot water to the boiler, so that boiler can deliver 100 to 185 degrees centigrade instead of 30. So that such a way that whatever the fuel that you are using in the boiler, such as LPG, CNG, or coal, or high-speed diesel, light diesel oil, LDO. So all these are very expensive fuels in these days. So we can save some of the operating savings over there by giving 90 degrees or 100 degrees hot water temperature to the boiler instead of sending 30 degrees. And similarly, chilled water for the air conditioning application. In community kitchen, where you can generate the hot water for the cooking application, and air conditioning for the chilled water, like for the air conditioning applications. In especially for the dairies also, you have a milk pasteurization is there, and CIP process is there. Similarly, for the poultry industries also, you have a defeathering, you require the hot water, you require the chilling water for the air conditioning. In industrial heat pump, obviously there is an industrial heat pump, means you can get 90 degrees or 100 degrees hot water temperature. uh, CO2, it is still possible, the cooling only also with the transcritical system, where you can have supermarkets like requirement, where you want to deliver minus 40 or minus 45 or minus 30 chill, freezing temperatures for the deep freezers and refrigeration and air conditioning applications also, it is possible. So transport cooling of the goods also it is possible, like truck refrigeration, ship refrigeration, container refrigeration. All these where you have a supply cold chain management. There we can be able to maintain minus 20 or minus 20 25 degrees cabin temperatures for the food that is going from one location to another location. You should be in cold chain. So there also it can be possible with the CO2. Mostly that is for the combined heating and cooling application, but subcritical systems where industrial refrigeration, you can be able to see that freezing up to minus 50 degrees centigrade also it is possible with ammonia. So that we can discuss in subsequent slides, where it is how advantageous a CO2 ammonia systems will be for the industries. So Danfoss has done very quite amount of work for delivering or developing the CO2 components. If you can see the cycle, all the this is the complex cycle where you can have multiple evaporation temperatures and multiple compressors, different pressures. So if you can see here, the cross marks. So these are the only four cross marks you can see here, such as IP receiver, accumulator, evaporators. So these are the only four components that is not having in our Danfoss portfolio, but remaining nearly 85 to 90% components which are ready for the CO2, and we are ready for the future to um, uh, uh, like um, give all the applications, all the components which is utilized for the CO2 application. For an example, we do have the compressors, we do have the VFDs, we do have the heat exchangers, which are rated for 130, 140 bar applications. We do have the high pressure expansion valve, ejectors, ball valves, evaporator controllers, superheat controllers, solenoid valves, expansion valves. Okay, pressure sensors, temperature sensors, main PLC, gas detection systems, system manager. So system manager is like a SCADA system manager. So all this, if you see in the right side, the low pressure switches, high pressure switches. So all are available in Danfoss portfolio to design any CO2 heat pump or CO2 chiller systems which are rated for high pressures. So one more thing here we need to understand is that like CO2 ammonia refrigerant in a cascade system. How CO2, for an example, if I want to operate instead of combined heating and cooling, uh, if you take an example of like fisheries industries, food processing industries, cold storage industries, dairies, ice cream industries. So all these industries in general operating at from starting from minus 25 to minus 30 degrees centigrade, all the way going down below to minus 45 degrees centigrade. Nowadays, we are using ammonia as a primary refrigerant for this all these industries because ammonia is cheap and it is having the one of the best thermodynamic properties and it is best for industry. But the only concern with ammonia is the it is toxic because whenever it is leaking to the atmosphere, so it is dangerous to human personals also. When the quantity of refrigerant is higher than one certain limit, uh, threshold limit. So that's where, per suppose if any plant, industrial plant, for an example, a food processing plant that is there in the urban area, in surrounding there is completely residential houses are there. In between, you have a food processing industry where we cannot able to use the ammonia as a main refrigerant. So in that case, we can consider CO2 as a best option in the lower side of the CO2 cascade system, so that all the plant, okay, where you have a maybe you can have 10 evaporators or 15 evaporators at your plant, all these evaporators will be run with CO2 in the plant side, so that there is all the whatever the charge that is there in the ammonia, all this charge we can be able to reduce. So only higher side only you can operate the ammonia. For an example, you can see this system. This system, there are three evaporators, okay, which is operating at maybe different temperatures. Okay, maybe one is operating at minus 40, another is operating at plus 5, so something like that. Okay, all these evaporators can be able to taken care by CO2 with this all this one, where from you can use the one HP receiver, one compressor, CO2 compressor, and LP receiver. So all this will be accumulated with CO2. Only the higher side, where you can see this is the higher side, correct? In this higher side only, you can use the ammonia as a refrigerant. So in this way, you can reduce nearly 90% of ammonia in the plant, so that it in a safe and secure operation will be possible with CO2 ammonia refrigeration system. So advantages also you can see the advantages of subcritical CO2 ammonia cascade system is properties of you can see the as we discussed the GWP is one, and it is a A1 refrigerant, and the pressures is the pressures and volumetric capacity. You can see the difference. The volumetric capacity, it is nearly 8,421 kilojoule per meter cube for CO2, where in other refrigerant is in 893 and 625. So that you can see the in comparison the saturation pressures also and volumetric cooling capacity also, it is nearly a, 3-4 times nearly 10 to 12 times higher than your ammonia, the volumetric cooling capacity at kilojoule per meter cube at minus 40 and minus 50. Uh, the refrigeration capacity is also, you can see here, the where you have an 134A refrigerant, ammonia refrigerant, CO2, the required compressor displacement. As we discussed, the CO2 compressor always allows the very small installations and compact footprint and low sizes, so that your shop floor area where you are, whatever the machine room area, okay, wherever the machine room area you have, that machine room area also will be very less compared to other refrigerant installations. So that is also one of the biggest advantage with CO2. So main advantages, if you can discuss the advantages of the CO2 ammonia cascade system over two-stage ammonia system, is what is like low operating cost, that is there, because it is having the superior cooling efficiency, particularly when you are operating at minus 35 and below. When you're operating at minus 35 and below, CO2 is one of the best refrigerant. It can give you a lot more advantages compared to any other refrigerant in the industry because of their thermophysical properties. And ammonia charge reduction, that we are already discussed, where you can reduce 90% ammonia charge when you're using CO2 is in the lower side, or ammonia is only contained at the higher side or cascade higher side. There you can reduce nearly 90% ammonia, so that the plant is safe whenever you are operating your plant in a residential areas or urban areas. As we discussed, the compact system, where you can have small CO2 compressor footprint, and obviously constant positive pressures. For an example, if you take ammonia when you are operating at minus 40, then you have to go to the vacuum. Okay, you have to go below the ambient pressures. In that case, air is a concern. Okay, when there is a smaller kind of leak, then air will obviously will enter into the system because of the pressure difference. So this kind of like challenges will be eliminated when you are operating at the CO2 in the lower side, because even if you are operating at the minus 40 or minus 45, the CO2 pressures will be at nearly more than 5 bar. Okay, then that point of time you cannot able to enter any air. It cannot able to enter any air into the system. The quality and throughput improvements. For an example, if I want to process in some shrimps or process in some fisheries, and this point of time, what will happen that like when the minus 40 or minus below minus 35, the heat transfer, the U values of the CO2 is way higher than any other refrigerant, so that it will give you very quick freezing to the material what you are freezing. For suppose in this application, you can consider as a shrimp. Okay, so that shrimp, the core temperature will be way, it is very nearer to the your evaporation temperatures. So such a way that the throughput will be high. Because of that higher heat transfer capabilities, you can increase the productivity also, so that you can instead of let's say 1000 kg per hour a system, it can deliver more than 1000 kg in an hour, because of that your freezing process is faster, your throughput is higher. And reduce the potential risk of food pollution. CO2 is non-toxic in nature, so that is where you can eliminate the potential risk of food pollution. So you can see the heat transfer properties as we discussed, where you can see with respect to the CO2 and ammonia. So ammonia, the heat transfer efficiency or overall heat transfer coefficients with respect to the temperature, where the temperatures are evaporation temperatures going from 20 degrees centigrade to minus 40 degrees centigrade. So almost the CO2 heat transfer efficiencies are almost in a constant. Okay, so that is the reason the thermophysical properties of the CO2 is way higher, very superior, and compared to all other refrigerant when you are operating the CO2 in below minus 35 degrees centigrade. So if you can see this one, the ammonia, the heat transfer capability is slowly reducing. It is going from plus 20 to minus 30. Any other like high cool temperate, ethylene glycol, temper or ethylene glycol or propylene glycol. So all these refrigerant. And similarly, if you are seeing in the right side also, CO2 versus propylene glycol. For suppose if I want to use a secondary refrigerant as propylene glycol instead of CO2, instead of if I use high cool as a secondary refrigerant as a brain in my system instead of CO2, then there is a lot of power consumption. There is a lot of compressor power, pump power will be there because of the higher viscosities of the propylene glycol and less thermodynamic superiority uh, against to the CO2. So you can see the calculations also where we can have CO2 can be savings can be there with operating savings can be there up to 15% with respect to the propylene glycol, and with respect to the high cool it is nearly 22% CO2 operating savings will be there if you are changing from propylene glycol to CO2 as a brine solution. So this is one of the cascade system efficiency indication. There you can see the CO2 coefficient refrigerant system performance with against to the ammonia and ammonia single stage, ammonia two stage, R22 single stage, R22 two stage, and ammonia CO2 cascade system. The ammonia cascade CO2 system is always higher. If you can see this one, the COP is always higher at -40 also. It is always higher at -50 also. If you can see here, 2.18 and 1.78. After that, you can get the ammonia two stage system as a more efficient one where you can have the 1.92 and 1.38. So Danfoss is also future ready for the CO2 components for the industrial applications as well. So where you are having like 1 megawatt plant or 2 megawatt plant. So all these plants it can be able to deliver with our CO2 future ready components. We are nearly 85 to 90% components are available in a Danfoss portfolio, which are like designed for the 140 bar rated applications also when you're dealing with the transcritical systems. But when you're dealing with the CO2 ammonia based systems where you are operating the CO2 in a subcritical, you can hardly design ratings will be 65 bar to 52 bar is more than sufficient. So those are the industrial components also which are available in Danfoss, so that if the requirements according to the requirement we can be able to design the system. Yeah, so this is it. I think this is the CO2 application where we are having thank you Azit for the opportunity that you have given to me. I think I believe I have like concluded my session within an hour. I hope so.
No, it was a fantastic session, but I'll tell you another, it was so informative. I was also completely involved in listening to you. I did not take my eyes off it because see what happens is, in an industry, cold chain is completely underserved, right?
Correct.
So
Yes,
there is
yes,
very little information, knowledge, and I think it was a brilliant session. And I have this strong feeling that there's a lot of people who want to know how the CO2 applications can
yes,
come
yes.
in and especially explore new opportunities in the
Exactly,
refrigeration.
exactly. Azit.
So it was
Thank
a
you very much.
brilliant session. Sorry, go ahead.
Thank you very much, Adit, like, for you giving me this opportunity to give more information about CO2 and how the technology is advancing, especially in cold chain, and what are the different kind of refrigerants which are which we are utilizing to generate the heat pump or the CO2 ammonia in scale, so that we can how our we can make India to a more of a green revolution or sustainability development side. We can reduce the fossil fuel consumption and all. So this is where Danfoss is also moving, so that we can be able to collaboratively we can share the knowledge to the industry, so that industry people are also more aware on these kind of new technologies, so that they will also start implementing in their industries on this new technology. So in a way it is a very I would like to thank you as well, because it is the more people know, so that they will more aware onto this technology, so that they can implement as a smaller step also more than sufficient to make the change. So thank you
We
Ajit.
will ensure that the entire RATA network will get to see this, and they will always have access to this video to train all their people to share this within their companies forever. And we owe it to you. Thank you very much for creating this content for us. Thank you
It's
so much.
my pleasure Ajit.
Thanks a lot. We will definitely get back to you and would love to have you again in our future
Definitely I
sessions.
will be there in any time, at any time Ajit.
Thank you very much. Thanks a lot.
Thank
Thank you.
thank you.
Thanks.
Bye. Bye.
From the land that celebrates innovation and breeds enterprise, comes the next chapter of India's HVAC and TAR journey. 3 cities, 4 milestones, 1 vision. RATA Conclave, India's most powerful platform for HVAC and our entrepreneurs, thinkers and changemakers. And now in 2026, we converge in Ahmedabad, the growth capital of the West, where business meets purpose and sustainability meets scale, empowering HVAC and our business for sustainable growth. 1,000 plus delegates, 70 plus industry speakers, 80 plus partners, 3 power-packed forums, national MSME awards, live networking and product showcases, a marketplace of ideas where innovation scales, connections deepen, and opportunities compound. Experience it all in the soul of Gujarat, culture, cuisine, and celebration. Only in Ahmedabad. Join the movement for MSAMS to thrive, manufacturers to evolve, and the ecosystem to advance. Mark your calendars, 25 and 26 September 2026.